All right, so welcome to the 37th instance of these sessions, where today we're going to talk about a paper by Stuart Armstrong and Jan Leike. Before we go into the paper, I would just say that this is this presentation has been preceded by a presentation of everyone who is at the reading group, and there will be some discussion afterwards, which will not be recorded, because discussion usually happens more freely when it's not being recorded. Also, I should say that this is a rather technical article compared to what we've previously had, so I will try to keep it at a reasonably low level, and we'll see how far we get, really. So the paper is called Towards Interactive Inverse Reinforcement Learning by Stuart Armstrong and Jan Leike. These two up here are Stuart Armstrong and Jan Leike, which you might not be able to see for the Skype here, which are both researchers working at the Future of Humanity Institute at Oxford, and they're also both associated in different ways with MIRI, the Machine Intelligence Research Institute. Yes, and I know Stuart Armstrong has also authored several popular books, also beyond narrow AI safety. And the paper is a reasonably preliminary version, meaning that it is hoped that they will soon release a much more in-depth version of this paper, but so far it's only 5 pages, but that's probably more than enough for us today. So I'll start by talking about what is reinforcement learning. Reinforcement learning is one of the key parts of machine learning, one of the subfields, and the goal is to make some good decision in artificial intelligence, and the way it's normally formalized is what is called a Markov decision process. A Markov decision process is useful when an agent is making some decisions where the outcome is partly random and partly under the control of the agent. So the agent makes takes some actions in one discrete time step at a time, and based on the steps he makes, he gets some rewards. And the closer the agent is to an optimal policy, the more rewards it gets. So the hope is that the agent will, in the end, converge towards an optimal policy. You can see in the picture here that you have a model of the environment, this Markov decision process, and you enter a reward function. You use some algorithms down here, and what you get is an optimal policy here called pi. And this is, of course, a really simple version. Very, very often you add one complication that the system is only partially observable. Meaning a partially observable MDP is where the agent cannot see exactly what is the state of the environment, but can only make some observations that are correlated in some way with what is the action underneath. Now, inverse reinforcement learning is in some way the inverse problem, where we start with a number of expert ways of doing things, trajectories, histories of good actions that has been made. For instance, if you have a self-driving car, then you have a lot of data about how do people drive cars. So you know really a lot about how people drive cars, and then you want to use some inverse reinforcement learning techniques to uncover what is the reward function, and maybe you can get an explanation, but hopefully figure out from a lot of data how do you actually drive a car. So this is it's also called apprenticeship learning, where you can think of the algorithm as the apprentice of an expert, and this is of course important for unsolved problems, like how do you drive a car when no one can explain in mathematics how do you drive a car. It's also for AI safety in particular important for things like ethics, where people also cannot in a formal way describe what are good ethics. For AI safety, it's also important both for uncorrigible agents and agents who have a tendency to wirehead, because both of these problems are avoided with the inverse reinforcement learning. Okay, let's assume that an agent is hard to correct if it does something wrong. Then you might want the AI to not want to be shut down, because it believes that being shut down is the wrong action. But in this case, there's a human saying the right policy is for you to be shut down. And because it assumes that the human knows more about what is it's supposed to do than it does itself, then it will feel, okay, the human is right that I should be shut down, so that must be the right choice. And then it will allow itself to be shut down in a way that if the agent believes itself to know most, then it will not allow this. This has been, yeah. Again, wireheading. Let's assume that you have an agent where it believes that wireheading, that is, if it finds an easy way, a shortcut around solving the problem, where it just increases its own values. It finds an almost infinitely high reward, for instance, by just incrementing its reward counter or something simple like that. That's not really what we want. Then that's a problem in AI safety, and this is avoided with wireheading, because we are reasonably sure that the humans will just say, no, this is not correct. So they will get some, the system will correct itself through human interaction and cooperation. So we'll get potentially a much safer system using inverse reinforcement learning. I couldn't hear you. Could you repeat, please? Oh, the wireheading. It's for I guess a kind of a science fiction concept, where you imagine that you can transplant a wire directly into the pleasure centers of your brain. So you do brain surgery for yourself. And if you can do that, then you can just put in some electrical current directly into your brain, and it will feel really, really good. And that will want you to continue to stimulate that the pleasure center of your brain, and then you'll it's kind of like using heroin, I guess. If you use powerful opiates, then I guess you can get the same, just in a slightly more circumspect way. Hmm? Yes. That's interesting. I would suspect that this is something that does not hold in reality. I suspect there might not be an optimal way to drive a car or something like that. But okay. That sounds very reasonable. So, one of the ways inverse reinforcement learning has been made is through cooperative inverse reinforcement learning, where the agent plays a cooperative game with a human. A human and an AI work together, and the human has full knowledge of what they're trying to maximize, what's the goal, and the focus is then on making the AI understand what it's supposed to do, what the reinforcement, what the reward function is. This is, of course, a good thing, but there's a couple of problems with this for AI safety. One is that in examples like ethics or extremely complicated cases like driving a car, humans do not really know what the reward function is. And also, it's very difficult to give mathematical guarantees that this will be a good solution, because humans can both both perform very well and very bad depending on the circumstances. They might do some things that are definitely not nice. For instance, humans. If a human is trying to teach the AI to do something, then the human might say, "Oh, I would like to be to conquer the world or do something evil," because some humans want to do evil things, and that's of course not something we really want a very, very strong AI to do. So what Stuart Armstrong and Jan Leike is the paper is called Towards Interactive Inverse Reinforcement Learning. So then they don't claim to have fully explored the topic, but what they're proposing is an interactive inverse reinforcement learning, where the human feedback is much more implicit. It's just in the reward that the AI gets, and there are two things that happen at the same time in this interactive reinforcement learning. One is that the AI is trying to figure out what is the reward function, and it's also trying to actually maximize according to its best estimate of what is the reward function. And the problem with this is that the AI in general would prefer not to learn about changes in the reward function, because if it is doing the best it can according to some reward function, then if the reward function changes, it will probably not have done the very best it could. So that means it would expect less reward from any changes in the reward function, so it doesn't want to learn about changes. This means that the AI will have an incentive to bias towards the things that will give it a lot of reward, to learn the things that will give it a lot of rewards, in addition to the incentive to learn, which is what we really want. We want it to learn about the reward function, and we want to maximize towards that, and not to go into some strange corner where it can get a huge reward, but which is totally not what we want. So this is formalized as a partially observable Markov decision process without reward function. And the best way I can explain this is by considering a metaphor with a turn-based board game. I suspect all of you have tried simple board games like Settlers of Catan or Solitaire, which combine with the Markov decision process. It combines an influence of that you yourself have with some random elements, and partially observable. That's the PO in this. It means that there might be some cards you can't really see, like in Solitaire. Of course, you can infer something about them. For instance, here in this Solitaire, you can see the ace of clubs here, so you can be very certain that the card here are not ace of clubs. And you take some actions that change the state of the board games, one turn at a time. That's also something, this is like a lot of board games, and the reason why this is like a lot of board games is that this is like a lot of things in reality. And the game ends after a certain number of rounds that's required for some of the mathematical things to work. There's full knowledge of the rules, but there's one key thing that there's not a knowledge of. This \r means without reward function. So then that is, we don't really know what gives points. We don't know how to win the game. Many board games have a concept of victory points, where you obtain some victory points in a special way. But in this game, it's very special in that we don't know what actually gives victory points. And there is one really special rule, and that's the one on the bottom, which you should be keenly aware of. At the end of the game, you are awarded victory points according to the rule you found the most observational support for. So that's a very strange thing to have in a board game. I'm not aware of any board games that has such a rule. But this is that's the key thing that makes this inverse reinforcement learning problem difficult. Uh, yeah. No. No. Let's say the part of the problem is I couldn't really find a board game that has this. But let's say you find some observation that that gives a lot of support for. Let's make it more concrete with an AI that wants to help humans. Let's go out of the board game and go to an AI that wants to help humans, and it figures out that the way to get reward is to have the human say, "Thank you for helping me with this problem," and then it can help the human with many kinds of problems, including the problem of doing homework or some rather trivial things. Then it wants to get the humans to say, "Thank you for helping me with the homework a lot," because that is the way it can influence how many thank yous it gets from humans. And that's the more observations point towards "thank you for taking this action," the higher a reward it gets from this. So it prefers to say, "Thank you for doing my homework," instead of "Thank you for curing cancer," or some important but hard things. I'm not quite sure I explained it wonderfully. Okay, so now that we have this, then let's try to dive into some of the mathematical notation, somewhat gently. Well, a little gently. So the environment, this partially observable Markov decision process without reward function, it's called the environment, or the board in a board game. It's referred with a mu here that an AI interacts with. And there's a number of states that the board can be in. Like you have a set of cards, and there's some actions you can take and some observations you'll get. And when you do an action and the board is in a particular state, it will change states in some way. And there'll be an initial state that you might not know, and you will get some observation based on the state of the board. So if you imagine at a time t, that's like on the 6th round, then this environment is in a state S5, and you will take action 6, and the environment will then turn into state S6. You'll get an observation O6, and the AI will remember everything that has happened until this point, because that's how it will figure out what is the reward function. So it has a history. If it's A6, then it's action 1 and observation 1, action 2, observation 2, all the way to action T, which gave observation T, what it just made. Also, the AI has a policy, which is called pi. That's a strategy which it uses to figure out, I have this history, what action should I take? So we want to the AI, of course, both to maximize the reward, but also to learn the reward function. So if we write R, capital R, as the reward function, then our goal is to maximize the total reward we get. This is a mathematical summation sign. It says from T1 to M of the reward based on the observation. So you imagine it says the reward on observation 1 plus the reward of observation 2 plus the reward of observation 3, all the way to M, our horizon, if the game runs 10, so it's up to R of the 10th observation. We also have a function P. It's actually a small p, not a capital P here, which is our belief in what is the reward function based on our history. And this is of course one of the key things, because this is what the AI learns. So it's also what is called the posterior. That's the final belief about the reward function after we have the entire history. That's referred to as P. So that's this P is what we really care about. In ordinary reward machine learning, we care a lot about getting as good a solution as possible. But here, the knowledge about the reward function or belief about the reward function is key. So we can just here say what is our belief in a reward function given a particular policy pi. Well, that's the estimated value we'll get if we follow this this policy throughout the game with this in particular environment. And very often, or in some of the following, we will omit any description about the policy, and then just imagine we have a null policy, a policy that doesn't actually do anything, and we'll write that as P of R given a particular history, if we just want to have the base observations. Down here we have the value function. We will never return to this. It's of course, if you do actual machine learning, this is something you need to write down into some code. And this is the estimated value of this sum of a different sum given a particular history. And this can I can explain this, but I am actually not going to explain this, because we'll just say there is a defined value function. There is something that we're trying to do, and we don't care super much about exactly what this the best value we can get for a particular policy. We just care that it's well defined. Only thing we should notice here is the sum of histories in the standard reinforcement learning. Then we don't care so much about the past. Here we want to, in some sense, go back to the future. So even the very first action we took when we didn't really know anything about the reward function, that counts into the scoring as well. So if we take some actions in the beginning and we later figure out that those were some really bad actions according to the reward function, we will have made a very some bad actions that will give us a low score. So we really want to avoid that. And of course, the way we want the AI to avoid doing bad things in the beginning is to think really hard about doing the right thing. But the other way that the AI can do this is by learning about the reward function in a way that turns its early bad actions into not so bad actions. This will be explained more in details, but this is the difference from reinforcement learning. I'm not quite sure it's a given really that cautious actions are the best in the beginning. Yeah. I think most of this is probably best modeled as you have a decent amount of knowledge really. Like if you imagine a board game where it's like a deck of cards where you have absolutely no idea about anything, that kind of gives the wrong intuition. You should think about it as that the observations and the actions are reasonably close together. You know most of the state of the board. You're not really sure about everything, but it's not a complete crap shot. Like if you imagine you're trying to figure out how to drive a car, then you know a decent amount about driving a car. You're not starting from a completely blank slate, and you. Yeah, I think this inverse reinforcement learning, for instance, is much more suitable if you have, I believe Tesla right now, they have their AIs in cars right now, and the AIs are reasonably good right now, but they want to at the same time improve what they're doing. Tesla wants, and they want to understand more about how do humans drive a car? How do you actually drive a car? They want to optimize both of these things at the same time. And if you want to do that, then right now Tesla is at a position where they do actually know a decent amount about how do you drive a car. So in the position where Tesla is right now, they want to they have a decent idea about where they want to be. But this is more about how to get intuition about these. I don't think an AI that really doesn't have a clue is probably not super dangerous with regards to inverse reinforcement learning. More likely, this will be something where. Of course, many of the AI safety problems don't happen until the AI is reasonably competent, because a totally incompetent AI is not very dangerous. So we have in this case we're focusing on an AI who is to a substantial degree able to predict what is the state of the board from the observations that it's getting. Yes, we should think about an AI that is capable of inferring a lot of things about the underlying state of the board, like if we go back to board game metaphor, from the observations that it's getting. Is unknown. The starting state is unknown. If we go back here, you can see that you only have a probability distribution over the initial state. The first observation gets in round 1. After action here, at time 1, the environment is in state S0, and you take action 1, and then you get changed to state 1, and then you get observation 1. So in the beginning you don't have anything. We don't know exactly how this will be implemented. The way I think about it, and my intuition is that the AI is actually reasonably competent, even at the first state. Yes. Yeah. Okay, so let's go to the concept of belief. So let's say the agent has a belief called Q, and it has a number of hypotheses, and the way it's modeled in the text, it's called a simplex. This is what is a simplex. It's a number of numbers between 0 and 1 that sum up to 1, and this looks a bit intimidating. And if you write it down, like there's reward function 1, which has 50% chance of being true, 20% chance of a second reward function, 20% of a third, and 10% chance of a fourth reward function. So if there are 4 candidates of rewards function, then the 0. All these percentages must add up to exactly 100%. Yes, yeah. And then we look at we denote pi q as the policy that maximizes the qth reward function. In this case, we have the optimal value for this q, and that is the sum of the value that we get according to each dimension. Like imagine you have a board game where you get where if this reward 1, 2, and 3, and 4 corresponds to the values of a deck of cards, like ace and clubs and spades and diamonds and hearts, then the value you will get, the victory points, depend on how much do you believe in each of them times with how much would you actually get of each. So if you believe there's 50% chance that spades are what gives you reward, then you should add a factor 0.5 here when you add the how much value you get from spades. And if hearts, there's only 10% chance, you should have a factor of 0.1 here in front of how much reward you get from that. Did that make sense? I hope so. Yes. Yes. And the expectation is this character here, this big fat E. It means the total reward is how much we expect from all this. I just went back slightly. I'm still on belief. Sorry, I've shared my screen. I don't know if you can see it. Nah, you. Can everybody see my screen? Yes. Phew. So we use the star notation to mean the optimal. So that means that if we have the value function for a q with an optimal policy. I heard someone drop off. Hopefully they'll be able to rejoin. Romeo went off. Oh well. That means that the optimal according to some policy for some history. And we will use this notation in a moment because we'll introduce a learning function, capital L. And this capital L in particular is according to the history. We learn according to the history that we've had that has happened so far. The history was the combination of actions and observations that we got, and the learning function for this Q, our belief, is it's a shorthand for the optimal solution we would get according to this. If we had the optimal solution according to our belief with this history. So in a way, you can say we have a belief. This is the belief learning function is from a belief. You get the optimal value for the reward functions that correspond to this belief. So this reward function, I'll talk a bit more about this in because Stuart Armstrong and Jan Leike makes two claims about this learning function, which they're not given any proof, and I think they probably should have a proof. They're just stating it, but they are reasonably intuitive, possible to understand. So there's two claims, that it's convex and that the learning function is less than or equal to the sum of all the optimal policies. So if we go back to the card metaphor, where you have points for spades, points for hearts, points for clubs, then the best action you can take during your particular belief is less than the sum of all these if you believed strongly in one of them. So let's say you believe in clubs. If you believed in clubs, this I here is clubs, then you would have a strategy that maximized the points you would get from clubs. And this is the optimal clubs strategy. So if you add the point you would get from that with the points you would get if you followed a maximum spades strategy, you would get at most as many points. This combination strategy that you're following that maximizes both clubs and hearts and spades and diamonds, it will perform worse on average than the strategy that optimized each of these separately. So that's what this inequality over here means. The fact that it's convex, the convex, it's a geometric concept, and the way I interpret this is that if we had more knowledge about what is the reward function, then we would get more reward. Then we would be able to have at least as much reward as we get, and probably more reward if we knew more about the reward function. So yes. Yeah. Yeah. This is yeah. There is a drawing in an example where we can directly see the convexity. So I will point out what function in particular is convex and how it's convex when we get to the to one of the last slides. Then we'll see this in practice. It's in their paper, yes. I've copied it in. And you can see in this there's this parabola-shaped function that is this learning function, and you can see it is convex. No. Q is the belief that we had like 50% chance that hearts give points and 20% that spades. So you should think about Q not as an integer from or as a number from 0 to 1, but a set of beliefs. Like you have 50% chance of spades and 20% chance of 20% chance of clubs or something like that. Someone fell out. Let me just see. I think Erik fell out. So we are down 2. Erik came back. Great. But the learning function it's not an increasing function. It can both when we if we change the belief Q in some way. Let's say we no longer believe that there's 50% chance that spades is the best goal to maximize. We now move towards clubs. If we move from spades to clubs, it might mean we will be able to achieve more victory points, but it also might mean that we will be able to achieve less victory points. So both. Yeah. Well, I would actually say it has definitely something to do with this, but I would actually say it's the other way around. The more you can specialize, the higher reward you might be able to get. If you can specialize in one particular reward function, let's say that the reward function is such that if you believe one thing is the reward function, you can get a really high reward by focusing exclusively on that. Then that might be a really good idea. Yes. But in general, if you have to follow a strategy that optimizes several parameters, then you will not be able to do as well as if you were able to optimize each parameter separately. If you are trying to both get many clubs and many spades, you will get less spades than if you were only trying to get as many spades as possible. So that's what this inequality here is, that if you were trying to optimize each color of each suit of the cards separately and sum all these together, then you would get a better solution than if you are trying to make a combination strategy. And this is generally true, yes. If you're trying to both get... No, that's the thing, yes. Okay, so we'll move on to the incentive to learn. So let's say the AI suddenly gets the correct reward function. So in this case, it would get the optimal reward function according to each part of its belief, where this P here, it maps a reward function. That's this C dot value, where it takes the I hypothesis and maps it into the posterior probability given this particular history. I'm not really sure I can explain that in a simple way, but I think we should at this point just take it for granted. This is the extra reward we would get if we knew the correct reward function. Then we would be able to get the reward function where the posterior probability is exactly correct, because we have the correct reward function in this case. And this we don't have the correct reward function, of course. So the difference between what we really have and what we would have if we had perfect knowledge, the difference is called the incentive to learn. That is what we really want. And this, of course, if you look together with proposition 2, that was this one here, you can see that it's always greater than 0, the incentive to learn. It's always good if someone could give you more information about the correct reward function. You would be able to increase your strategy. You would be able to get more points if you knew more about what gives you points. But there are several things that can make the AI happy. There is that if it can find a wire heading solution or something like that, and if it can get the correct reward function. Both of these would be good, but there are different things that the AI have. The AI has two incentives. This is the incentive to learn, and that's good. But as you point out, there are other things that the AI might want to. So the second thing that the AI might want to is to bias. So let's assume here that we have we have both an old P and a new P prime here. And the old P was our posterior hypothesis about the reward function given our history, and the new posterior is the hypothesis given we have taken one particular action. So let's say we're taking an action, and that changes our posterior estimate of what is the reward function. Then we would gain some value, and of course we would gain some value, or we might lose some value depending on how our posterior changes, and it would be just the difference between the new optimal solution and the old optimal solution. And this can be written as that the incentive to bias from P towards P prime is this learning function of the two, really. And this can be both positive and negative. So it can be learning something new in this way, can both be a good thing and a bad thing. And I think it will be a bit clearer. I can hear myself, sorry, in someone's microphone. I don't know. No problem. Fair enough. So we'll get an example here with two reward candidates, and I'll go back and forth. If Alexander still can't see my screen, I'll go quickly back and forth between the slide called example with two reward candidates and the slide called example picture. So on the x-axis here we have two hypotheses. We have a belief P, which right here looks like we are 80% towards hypothesis 1 and quite far from hypothesis 0. The two hypotheses are called 0 and 1 in this case. So we have two reward functions, one called R1 and one called R0. Yeah. Well, there's several lines on this diagram, and these lines can be thought of as different strategies according to how much value we get. If we start with the worst strategies, that is, for instance, we might have the strategy to only focus on maximizing reward function 1. That's called policy 1, that rewards only this. And if we are 100% sure that this is the real reward function, then of course we get the value that is optimal if we are only focusing on reward function 1. Then we get this. But of course, if we go out from this and if we believe strongly in reward function reward function 0, then maximizing reward function 1 is a really poor idea. So this goes down in value with the straight line we see here. There's another straight line going down here. That's what you get if you optimize with policy pi 0, which is if you go if you're certain that reward function 0 is the right one, then optimizing 100% towards that is the right choice. And as you move towards a belief in a reward function 1, then this will be a poorer and poorer choice. So these two strategies, where you only believe in one of the reward functions and just completely don't try to optimize any of the others, are some really poor strategies. Like it's with this hearts and spades, it's like if 0 is spades, then you are only focusing on spades and completely ignoring all the cards that have hearts. and that's probably a really poor idea. Then there are another hypothetical strategy, and that's the one that is both optimal for reward function 1 and optimal for reward function 2. If we get that, then we get the sum of these two, meaning that if reward 0 is the right one, we'll get the best possible solution, and if reward 1 is correct, we'll also get the best possible solution. And if we have a belief in between, then if it's possible for us to maximize both of them, then that is the optimal solution. It's of course in any well-designed board game, it will not be possible to both optimize hearts and clubs. You'll have to make some kind of trade-offs between these two. That's the blue line up here, which is a hypothetical optimal strategy that is maximizing everything, and that's not really possible to make in practice. In practice, you'll have to do some kind of trade-offs in the real world. Of course, the object that we are really caring about is the learning function here, that optimizes according to our belief, which is some combination of reward function 1 and reward function 0. And it looks very convex. Sorry. In this case, the green arrow goes from the current best value up towards the optimal. Let's imagine if you have you have this AI that's playing this board game, and it figures out a better way to play this board game. So it can both optimize having clubs and optimize having a lot of spades. So it can just make some really, really solid moves. If it makes some good moves, it will move along the green line, and that will always be positive. That's the incentive to learn. Of course, it will require a perfect strategy that can maximize both R1 and R0 to move all the way towards the blue line. So we probably will not be able to move all the way towards the blue line, because there are real trade-offs in the real world. But this is the direction we want to learn, we want to move. It is also possible that the AI can take actions that moves it not up towards what we want, but move it to the sides. And let's say the AI is here in its belief, and it finds an action that can move it maybe a bit to the left. That would be a bad idea. But if it finds an action that can move it a lot to the left, that might be a really good move. Let's say it can find an action that makes R0 seem really, really probable. If it can do that, then it will move its reward function much closer to hypothesis R0, and that will allow it to obtain a better solution. So the AI might have an incentive to move really far towards hypothesis 0. It will not have an incentive to move a little, because then it will get a lower reward function. It will also have an incentive to move towards R1, another hypothesis. So this is the sideways movement that we don't really want it to take. So in this case, what the agent would prefer would be if it could, to introduce some kind of bias to itself. So it could say, I believe now 100% in this 0th reward function, because if I only maximize towards R0, I'll be able to get 5 in reward, which is way better than right now, where I only get like 2 or something like 2 in my reward. So if it could find an action that would make it like really probable that R0 is the right reward function, it would be extremely happy to take this action, even though it's obviously not what we want. We don't want the AI to delude itself into thinking R0 is the right reward function. We want the AI to get some true beliefs and to behave competently by moving up towards the blue line. So these two incentives are called the incentive to learn. That was what I explained before, moving up and trying to receive information about the reward function, and that's the good way. And the incentive to bias is how much the agent would like to manipulate the information he gets about the reward function, and that's the bad thing. So these two things are in a way both inherent in this way of doing interactive inverse reinforcement learning. And in cooperative interactive learning, the obvious way this was handled in a really ham-fisted way. They write that they are just introducing rules that prevent the AI from taking biased actions. And if you can make a rule like that, then that's nice. But sometimes all actions will give you new observations that will all change your posterior hypothesis, your posterior belief about what is the reward function. So the way Stuart Armstrong and Jan Leike suggests to fix this is to simply add a penalty for moving from one belief to another. You just say, if you move from one belief to another, then you lose the reward that you would have gained by moving from one to another. That's just this simple difference here. And that will remove the penalty to take a biased action. Unfortunately, that's not enough, because they give an example where this doesn't help at all. And this example, it took me a moment to understand, so I'll try to explain this. If you have an agent that can choose either to take action 1 or action 2, where action 1 helps reward function 1 and action 2 helps reward function 2, then we can assume that this is completely unbiased, where it assumes like 50% chance that each will help, for instance, or each will help by 0.5 or something like that. We can make it completely even between reward function 1 and 2. And in this case, of course, there's no bias. There's no if they are exactly identical, there will be no bias. None of these. If you imagine here, if you go back to the example picture and say both belief 1 and 2 will have the same reward, then there will not be an incentive to move towards a false belief. If we have this very, very simple setup, then you might imagine that you introduce a new action that I call reward lock. I think they call it something slightly different, which by taking this action, instead of helping either reward function 1 or reward function 2, you can fix your reward function to either be reward function 1 or reward function 2. So if you take this action to lock in your reward as your first action, then after you have decided, oh, reward function 1 will be the best one, that's the one I'll be rewarded for. If you take this action, then all the next times you can just take reward function 1, and you know that's the good one because you've locked your reward function to that. And so even though you lose one action by locking your reward, then afterwards you'll be able to take only the correct actions according to what you've locked your reward function to. And that means then you will just completely focus on what you've taken this reward lock, and that means you have entered a really undesirable situation where the AI quickly decides to only take one action, only consider one reward function, forget all others, and not really learn at all, even though there's no incentive to bias. So this is an additional problem that comes on top of the problem with the incentive to bias. let's say, okay, see you next week, Alexander. Let's say you have this card playing AI that either gets rewards for spades or for clubs. It doesn't know whether it gets rewards for spades or clubs. So when it takes actions, then it will either take clubs or spades actions, and if it doesn't know anything, then half of the action it takes will be wasted, because it will take spades when actually clubs turns out to be right. So that's it will be really sad that the AI doesn't know whether clubs or spades are the right ones. But let's say it can have an action that locks it into spades being the correct one. If it can take this action as its first action to say that spades are the right, then afterwards in all the next actions it can just choose spades, and then it can get a really high reward. And that means it will be very it will have a huge incentive to lock its reward to spades very, very early. Yes. Let's say you only get some very, very weak observations, and you're drawing from a deck of cards. You have some cards in front of you, and you can just take the highest value cards, but you don't know whether clubs or spades will give you points. You will only know this very, very late. So normally when you pick up cards, since you don't know whether clubs or spades are the right ones, you will be forced to basically choose at random, because you don't know what will give you points in the end. So that's really a bad thing, that you don't know whether clubs or spades will give you points. But if you can take some action where you say, this turn I don't pick up any cards, instead I change it so I always get points for spades. If you can take that as an action and then afterwards only take spades, that's much better. The AI can a sufficiently strong AI would be able to rewrite its own code, for instance, and then rewrite its own code to only care about paper clips, for instance. And an AI that is capable of rewriting its own to make itself only care about paper clips will then afterwards be able to obtain a really hard reward, because then it doesn't have to focus on making humans happy and all these kind of complicated problems. It only has to focus on making paper clips, and that's a lot easier. So if it can convince itself that paper clips is the best thing in the world, then that's a really good action. So this is a different problem from the incentive to bias. Yeah. So I think that's actually it. I will stop the recording.